Hello and welcome to another Reigate Maths video focusing on the mechanics section of the second year A-level maths. This is Simon, and in this video we are going to be looking at the first half of the projectiles topic. This topic is all about projectile motion in 2 dimensions, so things like throwing a ball up in the air, throwing a ball off a cliff, that kind of thing. So in this video we're going to go through some examples that use numbers. In the next video, we'll be doing a similar thing, but deriving some formulae that you don't need to learn the formulae, but you need to know how to derive them. So what do we mean by projectiles? Well, as I said, something being thrown off a cliff, or a ball being kicked or thrown, that kind of thing. A gun being fired, things where something is moving through the air. Now, because we are doing kinematics, these are basically suvat questions. Okay, they are essentially at their core suvat. The key thing is that we're going to be doing suvat in 2 directions. Okay, we're going to be, like we've been doing with resolving forces, we're going to be doing suvat vertically, and we're going to be doing suvat horizontally. Now, there are some key things that you need to know. Sort of some key assumptions that you're probably not going to get told. That vertically, the acceleration part of suvat is 9.8 meters per second down. That is what we're going to be doing. Okay. Obviously, in terms of real life, this is not necessarily a particularly accurate assumption, but it's pretty good. The one that is less accurate is horizontally. Horizontally, we assume A is 0. Okay? Which means the horizontal component of velocity is the same at the start and finish. We do this so that the curve or the path of the ball fits a nice parabolic shape. Okay? Obviously, in real life, things like air resistance happen, or a ball, if you're kicking it, spins. So this is not going to be realistic in terms of the path of motion. The path of motion is more going to look like that. Okay, sort of dropping off, or maybe even sort of starting there and then spinning and going something along those lines. Okay, so these are the 2 major assumptions that we use for doing projectile questions. Okay, so no air resistance. Obviously, if you were to go and explore this idea further, maybe in a physics degree or just in physics, this is a decent starting point, and that's how mathematical modelling works. You start with a simple model, which this is, and then you add in more and more complications to make your model more and more accurate. So you'd start with something with no air resistance, and then you'd include air resistance later. Now, some important terminology is when we are talking about projectiles, the distance that something travels before it hits the ground is known as the range. Okay, so the range of a gun, or the range of the distance a golfer can hit a golf ball when it hits the ground, that is the range of the projectile. Okay, so it's, if you are asked for range, it's when the vertical height is when it hits the ground. The other thing as well, the time in both directions is the same. Because it takes the same amount of time to travel this distance as it does to travel this distance. We are not working in a TARDIS. Time does not pass differently depending on which direction you look at it. It's not how time works. So the time vertically and the time horizontally will be the same, which is really important later on. So what we're going to do is we're going to start looking at some examples, some relatively simple examples, just to kind of show you what's going on. And then we'll, as I said, in the second video, we'll basically do the same examples, just with no numbers. So this is the first example we're going to look at, and this is part A of it. So we've got a particle projected horizontally with a velocity of 15 meters per second. Find the horizontal and vertical components of displacement of the particle from the point of projection after 3 seconds. So first things first, let's think about drawing a diagram. So we're not told it's off a cliff, but it's projected horizontally, which means it's initially going this direction. Okay, so in terms of our diagram, let's draw it on a ledge, because otherwise it's just rolling along the floor, and that's not what happens. Okay, so we've got kind of this way. So we're told it's projected horizontally with 15 meters per second. And we're trying to find the horizontal and vertical components of displacement after 3 seconds. So first things first, let's write out our suvats. So drawing a diagram is incredibly useful with this type of question if you're not given a diagram already. If you are, go nuts labeling it. So I'm going to write my two suvats. I'm going to try and fit them in here so they're out of the way. We're going to have our vertical suvat. So let's go through this. So the distance vertically that we're trying to find is sy. The initial velocity vertically is 0 because we're told it's fired or it's kicked or it's projected horizontally, which means it's initially going only horizontally. No matter how quickly after it's projected it starts to move down, at the very point of projection, at the start, it's only moving horizontally. So the initial velocity vertically is 0. Now, I've taken up as positive because that's what I always do for these questions. If you're wanting to be a little bit more sensible with it and sort of think about the problem a little bit more, if we take down as positive, because moving down, that's probably going to be better actually. So let's with this one, let's take down as positive because it's moving downwards, which means that our acceleration is just g because it's going down, and we know that time is 3. Horizontally, we know that t is 3, and we're told it's projected horizontally at speed of 15. Because it's horizontal, we know that a is 0, so v is 15 as well, and s is sx. So this is now all of the information we need to finish answering this question. So what we're going to do is we're going to take each one in turn, and we're just going to do normal suvat to it. So we're going to go downwards, so we don't have v. So we're going to use the suvat equation that doesn't have v in, which is s equals ut plus a half at squared. To be honest, for projectiles, this is the equation you will probably use most often. This and v equals u plus at. Okay, these are the two equations that you will tend to use the most with projectiles. I'm not saying the other suvat equations won't get used, it's just not as common. And you can see, given that we've got a parabola shape, as I drew in the previous diagrams, it makes sense that we've got a squared here. It gives us that nice quadratic graph. So let's just put in all the bits we know. So ut, that's going to go to 0 because u is 0. So we've just got a half times g times 3 squared. So we get 9 over 2g, which we could obviously work out, but actually no, because we're trying to find the vertical component of displacement. So let's work that out. So it's going to be 9 times 4.9. So we got, 9 over 2 times 9.8. This gives us 44.1 meters. So it moves 44.1 meters down, which seems like a lot. But if you kick a football, it doesn't take long. So if you're thinking about a free kick, it doesn't take long for the free kick to get from the foot to the goal. It's a matter of half a second, maybe. depending on the distance of the free kick. So 3 seconds for a projectile is quite a long time. So we've got that. So we're going to go horizontally now. We're going to use the same equation because it's the one with S in. Okay, this term this time goes because it's A is 0. So we just get Sx is 15 times 3, which is 45. Okay, so it moves 45 meters across and 44.1 meters down. Part B is we are now going to find the distance from the point of projection after 3 seconds. So part B, we are finding this distance here. So it's just a case of using Pythagoras. So this is pi. Part B, distance equals 44.1 squared plus 45 squared, all square rooted, which again we type in our calculator. Oops. Square root the answer, and we get 63.0 meters. Okay, so a very, very simple projectiles question. So this second example we're going to look at is significantly quicker. A particle is projected with velocity u equals 3I plus 5j meters per second, where I and j are unit vectors in the horizontal and vertical directions respectively. Find the initial speed and the angle of projection. So when we're talking about projectiles, it's always working in 2 dimensions, which then introduces the idea of vectors. The fact that vectors in their nature give it in 2 dimensions makes this a very nice question. So we have the velocity, we want the speed. So speed, we know, is the magnitude of the velocity, which in this case is very easy to work out. 3 squared and 5 squared, all square rooted. It's going to be root 34. Which is 5.83 meters per second. The angle of projection, and we don't have to worry too much because we're going this way. So we've got 3 and 5. There's our angle. Tan alpha is opposite over adjacent. So our angle of projection is inverse tan 5 over 3. Now, make sure you're working in degrees. When you do mechanics, you almost exclusively work in degrees, unless you are specifically told otherwise. And we should say above I, just to make it very, very clear what we're doing. So this last example we're going to look at for this video is a much, much more typical projectiles exam type question. A projectile is launched from a point on horizontal ground with speed 150 meters per second at an angle of 10 degrees above the horizontal, and we want to find the time it takes for the projectile to reach its highest point. So let's draw a diagram just to see what's going on. As is really useful with a lot of mechanics, a diagram will help. So we've got our horizontal ground, and we've got our projectile doing this. And this is where it gets to its highest point. Okay, we know it's being projected with a speed, so we're not told the velocity, we're told the speed of 150 meters per second at an angle of 10 degrees. Now I know I haven't drawn an angle of 10 degrees, but I've labelled it, so it's fine. So we want to find time. So with this question, as we typically do with many questions of this type, let's write out our suvat equations. So we're going to go vertically, sorry, not equations, are variables. Suvat vertically and suvat horizontally. Now this time I am taking up as positive because that's the direction of motion. So S we don't know, We don't know the maximum height, so we can't fill anything in there. Our initial velocity, so this speed is 150, but that's at an angle. So we need to resolve our speed into its components. And we can see that the vertical component of this speed, is 150 sine 10. We'll come back to v, the acceleration. So it's been projected, and then all it's doing is slowing down. And so the acceleration is minus g. T is the thing we're trying to find. We don't actually need the horizontal part for part A. But that'll come in part B. So we'll come back to that and we'll fill that in later. So when it gets to its maximum point, if you look at it on one side, all that's happening with the ball, with the projectile, is it's doing this. Starts here, goes up, then goes down again. So the velocity, the vertical velocity at its highest point, is when it stops before it comes back down. So at its maximum point, the vertical velocity is 0. Now we've got this information, let's go about doing our part A. So we don't know S, so we use the suvat equation without S. V equals U plus AT. So V we know is 0, U is 150 sine 10, A is minus G, and we're trying to find time. So T is 150 sine 10 over 9.8, which we stick in our calculator. Oops, 150 sine 10 over 9.8, which gives us 2.66 seconds. Okay. So now we're going to get onto part B, and this is where this part A is not helpful. We know, because of what we've been saying, that the curve of this projectile is going to be symmetrical. We know that because conceptually that's what we're doing. But we don't know that for the maths. So we've basically got to start from scratch to do our part B. And part B is find the range of the projectile. I'm going to go through this the long way as well, because this may just be the question. Here's a projectiles thing, find the range. And if you know this method, it's actually much quicker than doing your part A, doubling the time to find the range. So, again, we've got our initial acceleration of 150, initial velocity of 150 and 10. And now our particle does this, and it stops. Okay, the range is where it hits the ground again. So this distance is what we're trying to find. So this is where doing suvat in two directions is important. Because this is the range. This is the thing we are trying to find. We know the initial velocity horizontally is 150 cos 10, and the initial velocity vertically is 150 sine 10. We've said that already. We also know that's there. The problem is, if we're just doing this question as is, we don't know the time. We need to work that out. Okay. So when you are working out the range, for range questions, most of the time you use the vertical to find time, then use the horizontal to find range. That's just typically the way you do these questions. Because don't forget, the range is where it hits the ground, or where it hits the level that it started on. Because we're hitting the level that we started on, let's look at the displacement vertically. We go up, but then we go back down, and in a vertical standpoint, we're back where we started. So the vertical displacement is 0. And we don't know the vertical velocity. We know the horizontal one, but there's no point putting it in because it's not actually that useful. So we're going to use the vertical one to find time. We don't know v, so resolving vertically, we know that s equals ut plus a half at squared. Don't forget, if you don't remember these suvat equations, it's not the end of the world because they're given to you in the formula book. So we know 0, we've got u is 150 sine t, sorry, sine 10, and it's times t, minus a half times 9.8 t squared. So we get that 4.9 t squared minus 150 sine 10 t equals 0. This is a quadratic equation, which we can factorize. And solve. We know we're not interested in t equals 0 because that's our starting point. So this is the value of t we want, which is going to be a horrible number, but oh well. It's the way this goes. And it confirms what we were saying before, that this is in fact double the time we found in the previous bit. But now we know time, we can now use that to find the range. So now going horizontally, we know again s equals ut plus a half at squared, but again conveniently a is 0. So the range, which is the thing we're trying to find, is u 150 cos 10 times the time we just found, 5.32. And we get that the range is 785 meters, which is a very long way. Okay, but if something's being projected at 150 meters per second, that's very fast. And in kind of that scheme of things, 5 seconds is a really long time for something moving that quickly. And we've found the range. So what else could we do? Well, we could find the velocity when it lands by working out the vertical component of velocity. The horizontal is the same as this, and then resolving forces. Resolving our velocity, and we'd probably find that it's 150. Other things they could do with this type of question, well, they could, instead of having it land and finding the range, they could put a platform. So this could be, when playing rugby, the ball is kicked from a spot kick to get a penalty. In rugby, it needs to get over the H, or over the bar of the H, to score a point. The bar of the H is a certain distance. Does it go over? And you set your vertical component to whatever the height is, and then do exactly this. So that's why I wanted to go through the longer method for finding the range, because this is much more adaptable than the previous question of just finding the time and doubling it, which works for this. But as soon as we start changing either our starting height or our finishing height, that's when that method doesn't work. But it's all about adapting this method here. And that's kind of it for projectiles, at least using number. In the next video, we'll be doing pretty much the same questions, but just using letters and using them to derive some formulae. But thank you for watching.